In this video, I'll go over how to balance chemical equations, and also go over a few other topics concerning writing chemical equations. Chemical reactions occur in specific ratios of reactants and products. The subject of chemistry dealing with the relationship between the relative quantities of the substances involved in a chemical reaction is called stoichiometry. Let's consider the Hindenburg reaction, dihydrogen reacting with dioxygen forming water. The reaction that I have here is not correctly formulated. This is because matter is not conserved. What we say is that this reaction is not balanced. We don't have the same numbers and types of atoms on the reactant side as we have on the product side. To balance this reaction, we need to put coefficients in front of the various molecules. Putting a 2 in front of dihydrogen and a 2 in front of water will balance this reaction. The 2 dihydrogens yield 4 hydrogens. The dioxygen yields 2 oxygens. The 2 waters yield 4 hydrogens and 2 oxygens. We now have the same number and types of atoms on the reactant side as we have on the product side. We've balanced this reaction. What I'm now going to do is I'm going to show you a systematic method by which you can balance chemical equations. I'll demonstrate this process by going through 2 examples. There are many ways to go about balancing chemical equations. I'm going to show you a more involved method that will always lead you to the correct answer. Once you have more practice balancing equations, you may stumble across shorter methods that will work for you. But for now, you may want to stick with this particular method. We're going to start with this unbalanced equation. Aluminum carbide reacting with water forming aluminum hydroxide plus methane, CH4. The first thing that you should do is write down your reactant molecules and your product molecules. The next step is to write down the number of atoms contained in each molecule, associating those atoms with the particular molecule. The next step is to connect where the atoms are going from your reactant side to your product side. So here we have the aluminum from the aluminum carbide going to the aluminum in the aluminum hydroxide. We have the carbon from the aluminum carbide going to the carbon in the methane. We have the hydrogens from the waters going to both molecules, and the oxygen from the water going only to the aluminum hydroxide. I find that it is easiest to start with one of the reactant molecules and balance the product molecules based on that reactant molecule, or vice versa. Here we have 4 aluminums on the reactant side and 1 aluminum on the product side. We also have 3 carbons on the reactant side and 1 carbon on the product side. In order to balance the number of atoms, we need to multiply all of the atoms in the aluminum hydroxide by 4 and all of the atoms in the methane by 3. Doing this yields 4 aluminum and 3 carbon on the product side, which matches the number of aluminum and carbon atoms on the reactant side. We're now going to go through and balance the hydrogens and oxygens, which are derived from the water. If we look at the total number of hydrogens and oxygens, we find that we have 24 hydrogens, 12 from the aluminum hydroxide and 12 from the methane, and 12 oxygens, all coming from the aluminum hydroxide. 24 to 12 is a 2 to 1 ratio. Water also has a 2 to 1 ratio. If we multiply the number of water molecules by 12, we now have 24 hydrogens and 12 oxygens. At this point, we have the same number and type of atoms on the reactant side as we have on the product side. We can go through and prove this to ourselves by canceling out atoms one by one. We have 4 aluminum on the reactant side. We have 4 aluminum on the product side. We have none left over on either. 3 carbon on the reactant, 3 carbon on the product. Once again, none left over. Going through, we find that's the case for the oxygens, and we find that's the case for the hydrogens. Our multiplication factors, 12, 4, and 3, represent the coefficients that we need to put in front of the molecules in this chemical equation. This, therefore, represents the balanced equation for this reaction. Here is another example. In this reaction, propane, C3H6, is going to react with dioxygen, forming carbon dioxide and water. Going through these steps, first, we write down the reactant molecules and the product molecules. We break down these molecules, associating the number of atoms with each particular molecule. We then connect reactants to products. Starting with the propane molecule and balancing the reactants and the products, we see that we have to multiply the number of carbon dioxides by 3. This will give us 3 carbons on the product side and 3 carbons on the reactant side. We also have to multiply the number of waters by 3. This will give us 6 hydrogens on the product side and 6 hydrogens on the reactant side. We're now going to go through and balance the oxygens. What we find is that we have a total of 9 oxygens on the product side and 2 oxygens on the reactant side. Therefore, we have to adjust the number of oxygens on the reactant side. In order to take those 2 oxygens and convert them into 9 oxygens, we have to multiply through by 9 halves. That 9 halves is not a physically meaningful number. Just like saying the current king of France is bald has no meaning, there is no current king of France. Saying that there's a half a molecule has no meaning. Molecules don't come in halves. In order to remove that 9 halves, we have to multiply through by 2. But if we multiply the O2 through by 2, we have to multiply everything through by 2. Doing this yields 6 carbons and 12 hydrogens on both sides of the reaction, and 18 oxygens on both sides of the reaction. We can prove this to ourselves by going through and canceling out all of the atoms. We see that there's no extra atoms on the reactant or the product side. In order to get the coefficients, we have to take our first series of coefficients and multiply them through by our second series of coefficients. Going through and doing this yields the balanced equation. In order to have a correctly formulated chemical equation, as we just said, the chemical equation must be balanced. There has to be the same number and type of atoms on the product and the reactant sides. In addition, it's also good practice to identify the physical states of products and reactants. This is because the physical state of a molecule can dictate how it reacts. Liquid dioxygen reacts differently than gaseous dioxygen. In order to do this, we identify the physical state in parentheses next to the molecules in the chemical equation. We use an S for a solid, an L for a liquid, a G for gas, and AQ for something that is dissolved in water. Fully formulating the above equations by putting in the physical states yields the following. O2 gas plus 2 NO gases yields 2 NO2 gases. Iron Cl3 dissolved in water plus 3 sodium hydroxides dissolved in water yields solid iron hydroxide and 3 sodium chlorides dissolved in water. 2 benzenes in the liquid state, C6H6 is benzene, plus 15 dioxygens in the gaseous state yield 12 carbon dioxides in the gaseous state, plus 6 H2Os in the liquid state. I'm now going to go a little off topic by talking about 3 basic reaction types. On the previous slide, we had benzene reacting with dioxygen, yielding carbon dioxide and water. This is an example of a combustion reaction. Combustion reactions are formally reactions that are highly exothermic, so they produce a lot of heat, wherein an oxidant reacts with a reactant, forming some gaseous products. A large subset of these reactions involve dioxygen reacting with hydrocarbons, yielding carbon dioxide, water, heat, and other products. This is the reaction that takes place in an internal combustion engine. Another common type of reaction is a combination reaction. A combination reaction is a reaction where 2 reactants combine to form one product. An example of this is dinitrogen plus 3 dihydrogens, forming 2 ammonia. This is an incredibly important industrial reaction. It produces the vast majority of fertilizer used in agriculture. A third type of reaction is a decomposition reaction. A decomposition reaction is the opposite of a combination reaction. One reactant is breaking down into 2 products. An example of this reaction is 2 sodium azides forming 2 sodiums plus 3 dinitrogens. This is the reaction that inflates the airbag in a car. Sodium azide rapidly reacts, producing a large quantity of N2 gas, which inflates the airbag. And with that, we've reached the end of this video. The key takeaways are that all chemical reactions must be balanced. You are shown a straightforward method to balance chemical equations. A fully formulated chemical equation includes the physical states of the reactants and products. And 3 broad classes of chemical reactions include combustion reactions, combination reactions, and decomposition reactions. In the next video, we'll go over the concepts of the mole and molar mass.